They said it couldn't be done. A radio transmitter small enough to fit inside an artillery shell, rugged enough to survive being fired from a gun at accelerations that would crush a man to paste, reliable enough to function after spinning at 14,000 revolutions per minute, and cheap enough to be expendable. The physicists at the Naval Ordnance Laboratory knew the engineering challenges. They also knew that if they failed, American sailors would continue dying under attacks from aircraft that anti-aircraft guns simply could not hit. The morning of January 5, 1943, off the coast of Guadalcanal, the destroyer USS Helena opened fire on incoming Japanese aircraft. Her 5-inch 38 caliber guns hurled shells into the sky at a rate of 15 rounds per minute per gun. Each shell was fitted with a mechanical time fuse, set before firing to detonate at a predetermined altitude. The gunners had calculated the enemy aircraft's speed, altitude, approach angle. They had set their fuses accordingly. They had done everything their training demanded. The shells exploded in the sky, creating dark bursts of shrapnel at the altitudes where the aircraft should have been. But the aircraft were not there. They had changed altitude, or the initial calculations were slightly wrong, or the fuse timing was imprecise by even a fraction of a second. The shells exploded harmlessly, too high or too low, or too far ahead or too far behind. The Japanese planes continued their attack runs. This was the fundamental problem of anti-aircraft warfare in 1943. Hitting a moving aircraft with an explosive shell required the shell to detonate at precisely the right moment in three-dimensional space. A direct hit was possible, but extraordinarily unlikely. The standard solution was the barrage, filling a volume of sky with shrapnel and hoping the enemy flew through it. But this required enormous quantities of ammunition and still achieved disappointingly low kill rates. American naval commanders knew the statistics. In the early months of the Pacific War, it took an average of 2,500 rounds of 5-inch ammunition to bring down a single enemy aircraft. Some engagements required far more. The expenditure was staggering, both in terms of ammunition consumed and in the simple fact that ships had limited magazine space. A destroyer carried perhaps 1,500 rounds of 5-inch ammunition. If the statistics held, she could expect to destroy less than one aircraft before running dry. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Japanese knew this too. Their pilots understood that American anti-aircraft fire was impressive to watch, the sky filled with black bursts and tracer rounds, but statistically survivable. They pressed their attacks, accepting casualties, but knowing that most aircraft would get through. For kamikaze pilots in the later years of the war, the calculus was even simpler. They only needed to survive long enough to reach their target. Anti-aircraft fire that failed to destroy them immediately had failed entirely. The problem was not new. Anti-aircraft warfare had existed since the First World War, when aircraft first became significant military threats. Gunners had been trying to hit moving aircraft for decades. They had developed increasingly sophisticated mechanical computers to calculate firing solutions. They had improved their gun designs, increasing muzzle velocities and rates of fire. They had trained their crews to extraordinary levels of proficiency. But they still faced the same fundamental challenge. The shell had to detonate at exactly the right place at exactly the right time. And in 1943, that meant setting a mechanical time fuse before firing, essentially predicting the future and hoping the prediction was correct. American losses to air attack were mounting. At Guadalcanal, at the Battle of the Santa Cruz Islands, at dozens of smaller engagements, Japanese aircraft broke through the anti-aircraft defenses and struck ships. The carrier USS Hornet went down after repeated bomb and torpedo hits. The carrier USS Wasp was torpedoed and sank. Cruisers, destroyers, transports, all were vulnerable. The 5-inch guns fired until their barrels were too hot to touch, expending thousands of rounds, but the aircraft kept coming. The mechanical time fuse had been the standard solution for anti-aircraft warfare since the early 20th century. The principle was simple, almost crude. Before loading a shell into the gun, a crew member would set a mechanical timer built into the fuse. This timer, driven by a spring or powder train, would count down during the shell's flight. When the timer reached 0, it would trigger the detonator, exploding the shell and sending shrapnel in all directions. The Mark 43 mechanical time fuse, standard on American 5-inch anti-aircraft ammunition in the early years of the war, was a precision instrument by the standards of its time. It contained a clockwork mechanism with gears, springs, and a powder train. The fuse setter, a specialized tool mounted near the gun, would adjust the timing mechanism to the calculated flight time. The gunners had to estimate the range to the target, calculate the shell's flight time based on its muzzle velocity and trajectory, and set the fuse accordingly. All of this had to happen in seconds while the aircraft approached at several hundred miles per hour. The system's limitations were obvious to anyone who used it. First, it required accurate range estimation. Optical rangefinders could provide this, but they were affected by visibility, by the operator's skill, by the simple fact that aircraft could change altitude and direction. Second, it required accurate calculation. Mechanical computers like the Mark 37 director system helped, feeding bearing and elevation data to the guns, but they were solving complex three-dimensional trajectory problems in real time, with mechanical gears and cams. Third, it required that the aircraft continue flying the path predicted by the calculations. If the pilot saw the anti-aircraft fire and maneuvered, the carefully calculated firing solution became worthless. Fourth, and perhaps most fundamentally, the mechanical time fuse itself had limitations. The timing mechanism had to be robust enough to survive being fired from a gun. A 5-inch 38 shell experienced acceleration forces of 20,000 times the force of gravity when fired. This was enough to flatten any delicate mechanism. The fuse had to be simple, rugged, and reliable. But simplicity meant limited precision. Even under perfect conditions, mechanical time fuses had timing variations of several hundredths of a second. At shell velocities of 2,500 feet per second, that translated to uncertainties of dozens of feet in detonation position. The result was that anti-aircraft fire was fundamentally imprecise. Gunners created zones of shrapnel in the sky, hoping the enemy would fly through them. Against tight formations of bombers flying steady courses, this could be effective. Against single aircraft or small groups making evasive maneuvers, it was largely ineffective. The numbers told the story. In European theatre operations, American and British anti-aircraft batteries firing at German aircraft achieved kill rates that required thousands of rounds per aircraft destroyed. In the Pacific, the statistics were similarly grim. Navy researchers had recognized the problem before the war began. In 1938, at a meeting of the Naval Research Advisory Committee, scientists and military officers discussed the future of naval warfare. Aircraft were becoming faster and more capable. Carriers were becoming more important. Anti-aircraft defense was critical, yet the existing technology was clearly inadequate. One scientist at that meeting was Merle Tuve, a physicist who had been working at the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. Tuve had spent the 1930s developing radio equipment for high-altitude research. He had sent radio transmitters into the upper atmosphere aboard balloons and studied how radio waves propagated through the ionosphere. He understood radio technology at a level few people in the world could match, and he understood that radio waves could detect aircraft. The British were already developing radar for this purpose, but Tuve saw a different possibility. If radio waves could detect an aircraft, perhaps they could also tell a shell when it was close enough to that aircraft to detonate effectively. The concept was straightforward in theory. Put a small radio transmitter inside the shell. Have it send out radio waves as the shell flew. When those radio waves bounced back from a nearby aircraft, the reflected signal would trigger the detonator. The shell would explode when it was actually close to its target, not when a mechanical timer guessed it should be close. The idea was not entirely new. Scientists in Britain had proposed similar concepts. German researchers had explored the possibility, but everyone who examined the problem seriously reached the same conclusion. The engineering challenges were overwhelming. Building a radio transmitter small enough to fit inside a shell casing was difficult but possible. Making that transmitter survive the shock of being fired was a different matter entirely. When a 5-inch shell is fired, it experiences acceleration that peaks at approximately 20,000 times the acceleration of gravity. This happens in the first few milliseconds as the shell travels down the gun barrel. For comparison, a human being loses consciousness at accelerations above 10 times gravity. Fighter pilots, in tight turns, might experience 8 or 9 times gravity for a few seconds. 20,000 times gravity was not a force. It was violence. Any component inside the shell had to survive this violence without breaking, without shifting position, without losing electrical connections. Radio tubes, the vacuum tubes that formed the heart of any radio transmitter in the 1940s, were fragile glass envelopes containing delicate metal filaments and grids. They were designed to sit in radio sets or laboratory equipment, not to be shot from guns. The consensus among engineers who examined the problem was that vacuum tubes simply could not survive being fired. They would shatter, the filaments would break, the entire concept was impractical. Then there was the question of power. A radio transmitter needs electrical power. In a normal radio set, this comes from batteries or the electrical mains. But a shell fired from a gun spins rapidly due to the rifling in the barrel. A 5-inch shell rotates at approximately 14,000 revolutions per minute. At this spin rate, any liquid battery would be torn apart by centrifugal forces. Conventional batteries using liquid electrolytes were impossible. The transmitter also had to be small. The interior of a 5-inch shell, after accounting for the space needed for the explosive charge and the mechanical components of the fuse, provided perhaps 4 cubic inches of space. The entire radio system, transmitter, receiver, power supply, detonator circuit, everything had to fit in a volume roughly the size of a coffee cup. It had to be cheap. This was perhaps the most demanding requirement. A proximity fuse was by definition expendable. Every shell fired would consume 1 fuse. If the fuses cost hundreds of dollars each, the ammunition would be prohibitively expensive. The entire point was to improve the efficiency of anti-aircraft fire, not to make it economically impossible. The target cost was roughly equivalent to the cost of the shell itself, perhaps $25 in 1940 dollars. For that price, they needed to build a miniature radio that could survive being shot from a gun, and it had to be reliable. A mechanical time fuse that failed simply didn't detonate, resulting in a dud shell. Annoying, but not catastrophic. A proximity fuse that failed at the wrong moment could detonate prematurely, possibly while the shell was still in the gun barrel or just after leaving the muzzle. This would destroy the gun and kill the crew. The safety requirements were absolute. The fuse had to remain inert through handling, loading, and the initial moments of flight. It had to arm itself only after the shell had travelled safely away from the ship. And then it had to function reliably, detecting nearby aircraft and detonating at the right moment. These were not merely difficult engineering challenges. They were challenges that most engineers in 1938 believed were fundamentally impossible to solve with existing technology. Radio equipment was large, fragile, and expensive. Miniaturization techniques were primitive. Solid-state electronics did not exist. Integrated circuits would not be invented for another 2 decades. The tools available to engineers in the late 1930s were vacuum tubes, resistors, capacitors, and mechanical components. Building a working proximity fuse with these tools seemed like fantasy. But Merle Tuve and the scientists at the Naval Ordnance Laboratory believed it could be done. They had to believe it could be done, because the alternative was accepting that anti-aircraft defense would remain ineffective, that American ships would continue to die under air attack, that thousands of sailors would be killed because the shells defending them could not reliably hit their targets. The stakes were high enough that even an apparently impossible engineering challenge was worth attempting. In the summer of 1940, as German, Bombs fell on London and the Battle of Britain raged. Merle Tuve received authorization to begin serious research on the proximity fuse problem. The National Defense Research Committee, a new organization created to coordinate scientific work for military applications, assigned the project to Section T, based at the Department of Terrestrial Magnetism in Washington. Tuve would lead the effort. He assembled a team of physicists and engineers, many of them young men who had been working on radio research or ionospheric studies. The first decision was fundamental. They would use vacuum tubes despite everyone's certainty that vacuum tubes could not survive being fired from a gun. Tuve's reasoning was simple. Vacuum tubes were the only technology available that could amplify radio signals and switch electrical circuits at the speeds required. If vacuum tubes couldn't work, nothing would work. Therefore, they had to make vacuum tubes work. The team began by testing commercial vacuum tubes, the kind used in ordinary radio sets. They built a device that could simulate the acceleration forces of being fired from a gun. The device used a compressed air gun to accelerate test fixtures at high velocities, subjecting the tubes to shock loads similar to what they would experience in actual firing. Every commercial tube they tested failed immediately. The glass envelopes shattered, the filaments broke, the internal structures collapsed. This confirmed what everyone already believed, but it also provided data. The team could see exactly how the tubes failed. The filaments broke because they were too long and too thin, designed for efficiency in normal radio applications, but fundamentally too fragile for this environment. The glass envelopes cracked because the internal structures weren't supported properly. The getter material, a reactive substance used to maintain the vacuum inside the tube, broke loose and contaminated the electrodes. Engineers at the Raytheon Manufacturing Company in Massachusetts, working under contract to Section T, began redesigning vacuum tubes specifically for the proximity fuse. They shortened the filaments, making them stubbier and more robust. They increased the diameter of the support wires. They changed the glass formulation to make it more resistant to shock. They redesigned the internal structure to distribute stress more evenly. They tested each modification in the airgun apparatus. By December 1940, they had tubes that survived the shock test. Not reliably, not consistently, but some tubes survived. This was progress. Throughout 1941, the engineers continued refining the design. They discovered that the getter material had to be secured differently to prevent it from breaking loose. They found that certain glass formulations worked better than others. They learned that the electrodes needed reinforcement at specific stress points. The final design, designated the Type WW58A tube, bore little a resemblance to commercial vacuum tubes. It was smaller, measuring about 1.5 inches tall and 0.5 inch in diameter. The internal structure was heavily reinforced. The filament was short and thick. The glass envelope was specially formulated for shock resistance. In testing, these tubes survived accelerations of 25,000 times gravity, higher than they would experience in actual firing. The survival rate reached 95%, but a vacuum tube alone was not a proximity fuse. The tube needed to be part of a complete radio circuit. That circuit needed a power supply. The team chose a battery design that used no liquid electrolytes. Instead, they developed a dry battery using reserve electrolyte that would be released by centrifugal force when the shell spun. As the shell rotated at 14,000 revolutions per minute, the spinning motion would force the electrolyte into contact with the battery plates, activating the battery. Before firing, the battery was inert. After firing, the spin activated it. This solved both the power problem and part of the safety problem. The radio circuit itself was remarkably simple by necessity. It had to fit in 4 cubic inches and use only 5 vacuum tubes, the Type WW58A tubes they had developed. The circuit was a radio altimeter, essentially. It transmitted a continuous radio frequency signal. When that signal reflected off a nearby object, the reflected wave would interfere with the transmitted wave, creating a beat frequency. This beat frequency would increase as the shell got closer to the reflecting object. When the beat frequency reached a certain threshold, indicating the shell was within lethal range, the circuit would trigger the detonator. The team tested the circuit extensively on the ground, using mock-ups and laboratory equipment. They tested it in non-rotating conditions, verifying that the radio worked and could detect nearby objects. Then they tested it while spinning, mounting the entire assembly on a centrifuge to simulate the rotation of a shell in flight. The circuit continued to function. The tubes survived. The battery activated properly. By the spring of 1942, they had a design that worked in the laboratory. Now they needed to test it by actually firing it from a gun. The proving ground at Dahlgren, Virginia, became the test site. Engineers mounted prototype fuses in 5-inch shells and loaded them into a test gun. They set up radar reflectors at various distances downrange to serve as targets. On the first test firing, the shell exploded prematurely, less than 100 yards from the gun. The safety mechanism had failed. The premature detonation sent engineers back to their workbenches. The safety mechanism was critical. The fuse had to remain completely inert during handling and loading. It had to arm itself only after the shell had travelled at least 300 yards from the gun, far enough that a premature detonation would not endanger the gun crew. The arming mechanism they had designed used a mechanical system that should have kept the detonator circuit disconnected until centrifugal force, after several seconds of flight, closed the arming switch. Analysis of the failed test showed that the arming switch had closed too early, probably due to the shock of firing rather than the intended centrifugal delay. The engineers redesigned the arming mechanism, adding redundant safety features. They added a second mechanical delay that required the shell to make a certain number of rotations before arming could occur. They added a third safety that required the shell to experience a minimum sustained acceleration, which would only occur during flight, not during handling. Testing resumed. The next series of test firings showed better results. Some shells exploded at the correct distance when passing near the radar reflectors. Some failed to detonate at all. Some detonated randomly at incorrect distances. The success rate was perhaps 20%. This was not adequate for operational use, but it proved the concept worked. A shell could detect a nearby object using radio waves and detonate itself at the appropriate moment. Throughout the summer and fall of 1942, the team at Section T and the engineers at Raytheon continued refining the design. They discovered that temperature variations affected the battery performance. Shells stored in cold magazines and then fired through hot gun barrels experienced thermal stresses that affected battery activation. They developed thermal insulation for the battery compartment. They discovered that the radio frequency oscillator could drift during flight, affecting detection sensitivity. They improved the oscillator stability. They discovered that the detonator circuit sometimes triggered on electrical noise from the radio transmitter itself. They added better filtering and shielding. Each problem required investigation, analysis, redesign, and retesting. Each solution added complexity to a device that needed to be simple and manufacturable in large quantities. By January 1943, the reliability rate had improved to 70%. 7 out of 10 test rounds detonated when passing near a target. This was still not ideal, but it was approaching operational usefulness. The Navy wanted to begin production. The urgency was intense. American ships were being lost to air attack throughout the Pacific. Every week of delay meant more casualties. But moving from laboratory prototypes to mass production presented another set of challenges entirely. The proximity fuse was complex. It contained 5 vacuum tubes, each one a precision device requiring careful assembly. It contained the battery system with its reserve electrolyte mechanism. It contained the radio circuit with its resistors, capacitors, and inductors, all of which had to be miniature versions designed to fit in the cramped space. It contained the mechanical safety and arming mechanisms. It contained the detonator and booster charge. Assembly required skilled workers following precise procedures. The vacuum tubes had to be inserted carefully to avoid damage. The radio circuit components had to be soldered with exact techniques to ensure they would survive the firing shock. The battery had to be filled with its reserve electrolyte and sealed perfectly. The safety mechanisms had to be assembled with tolerances measured in thousandths of an inch, and all of this had to be done at a cost of roughly $25 per fuse in 1943 dollars. The Eastman Kodak Company received a contract to manufacture the fuzzes at their facilities in Rochester, New York. Kodak had expertise in precision manufacturing from their camera and optical equipment production. They built new factory space specifically for fuse production. They hired and trained workers, many of them women who had never worked in manufacturing before. They developed assembly line techniques to handle the complex construction. Production began slowly in late 1942. The first batches had high defect rates as workers learned the procedures and as manufacturing techniques were refined. By early 1943, production was reaching several thousand fuses per week. By mid-1943, weekly production exceeded 10,000. The fuses were designated Mark 32 for 5-inch shells and later Mark 53 for other applications. Security around the program was extraordinary. The proximity fuse was classified at the highest level. It was considered more secret than the atomic bomb program in the early years of the war. The reason was simple. If the Germans or Japanese captured an intact fuse and reverse-engineered it, they could develop their own versions. German anti-aircraft defenses were already formidable. Giving them proximity fuzzes would make Allied bombing campaigns vastly more dangerous. The Allies also feared that if the Germans understood the technology, they might develop countermeasures, jamming systems that could prevent the fuses from functioning. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Therefore, strict rules governed the use of proximity fuses. They could only be fired over water, where duds would sink and could not be recovered by the enemy. They could not be used over land in Europe until late in the war, when the military situation made capture by German forces unlikely. Every ship that carried proximity-fused ammunition received special security briefings. Gun crews were told the ammunition was secret, but were not told how it worked or why it was special. The first combat use of the proximity fuse occurred on January 5, 1943, in exactly the circumstances described at the beginning of this account. The destroyer USS Helena, operating off Guadalcanal, engaged Japanese aircraft using 5-inch shells fitted with the new Mark 32 proximity fuzzes. The gun crews had been issued the special ammunition without explanation. They had been told to use it against aircraft targets and had been warned that the ammunition was highly classified. When the Japanese aircraft appeared, Helena's gunnery officer ordered the crews to commence firing. The 5-inch guns began their familiar rhythm, hurling shells skyward. But what happened next was completely unfamiliar to everyone watching. The shells exploded near the aircraft. Not in empty air, where mechanical time fuses had calculated they should explode, but actually near the aircraft. When a shell passed within 70 feet of a plane, it detonated automatically, sending shrapnel through the space the plane occupied. The first aircraft took hits and began trailing smoke. It lost altitude and crashed into the sea. The second aircraft maneuvered, but the following shells tracked it, exploding nearby. More hits. The aircraft lost a wing and tumbled into the water. In less than 2 minutes, Helena had destroyed 2 aircraft with approximately 50 rounds of ammunition. Under the old system, with mechanical time fuses, this would have required hundreds or thousands of rounds and might not have achieved any kills at all. The gun crews stared at each other in confusion. Something was different about this ammunition. It was hitting targets. The gunnery officer, who had been briefed on the general nature of the proximity fuse but not its specific operation, watched the engagement with satisfaction mixed with concern. The ammunition worked, clearly, but he had been ordered not to discuss it with anyone, not even to confirm to his own crew that anything unusual had happened. Word spread through the ship anyway. Sailors talk. Gun crews compared notes. Everyone who had witnessed the engagement agreed that something about the ammunition was different. The shells were exploding at exactly the right moments. The hit rate was impossible by previous standards. Speculation ran through the crew quarters. Some sailors thought the shells had some kind of magnetic detector that sensed metal aircraft. Others thought there was a new kind of explosive that was more powerful. A few guessed something closer to the truth, that radio was involved somehow. Similar results occurred in subsequent engagements. The cruiser USS Cleveland used proximity fuzzes against Japanese aircraft in the Solomon Islands in February 1943. She achieved multiple kills with ammunition expenditure far below previous averages. The battleship USS South Dakota used proximity fuses during operations near Bougainville. Her 5-inch batteries destroyed attacking aircraft with unprecedented efficiency. The cruiser USS San Diego, which would eventually be credited with shooting down more Japanese aircraft than any other ship in the Pacific, relied heavily on proximity-fused ammunition for her success. The statistics were compelling. Ships using proximity fuzzes required an average of approximately 300 rounds per aircraft destroyed, compared to the previous average of 2,500 rounds with mechanical time fuzzes. This was not a marginal improvement. This was a fundamental revolution in anti-aircraft warfare. A ship's limited ammunition supply, which previously might have allowed her to destroy 1 or 2 aircraft before running dry, could now potentially destroy 10 or 15 aircraft. The strategic implications were enormous. Japanese pilots began noticing the change in American anti-aircraft fire. They could not identify what was different, but they observed that American ships were achieving better results. Shells were exploding closer to attacking aircraft. Hit rates were increasing. Losses were mounting. Japanese tactical doctrine adapted by emphasizing even more aggressive attacks, trying to penetrate the anti-aircraft zone as quickly as possible to minimize exposure. But this played into American hands, because proximity fuzzes were most effective against fast-moving targets making aggressive approaches. The psychological effect on American sailors was equally significant. Anti-aircraft duty had been frustrating. Crews fired thousands of rounds and rarely saw confirmed kills. They watched their ships damaged or sunk by aircraft that penetrated their defenses despite their best efforts. Now they were hitting targets. The guns they manned were actually effective. Morale in anti-aircraft crews improved noticeably. Men who had felt helpless against air attack now felt they could fight back effectively. But the full potential of the proximity fuse would not be revealed in naval combat. That would come later, in a completely different environment, when the technology was adapted for a weapon system no one had originally anticipated. The proximity fuse had been designed for anti-aircraft defense. It would prove equally revolutionary in an offensive role, one that would change the nature of artillery warfare and terrify soldiers who found themselves on the receiving end. The proximity fuse's success in naval anti-aircraft warfare was remarkable enough to justify the entire development effort. Ships that had been vulnerable to air attack now had effective defenses. American carrier task forces could operate with greater confidence, knowing their screening vessels could actually shoot down attacking aircraft. The statistical improvement, from 2,500 rounds per kill to 300 rounds per kill, meant that a ship's ammunition supply lasted through extended engagements instead of being exhausted after the first few attacks. But in late 1943, artillery officers in Europe began asking a provocative question. If the proximity fuse could detect an aircraft and detonate when nearby, could it detect the ground? And if it could detect the ground, could artillery shells be fused to explode at a set height above the ground, creating an airburst effect that would be devastating against infantry and light vehicles? The concept of airburst artillery was not new. Artillery forces had used time fuses to create airbursts for decades. A shell, exploding 20 or 30 feet above the ground, sprayed shrapnel downward in a cone, covering a much larger area than a shell exploding on impact. Soldiers in foxholes or trenches were vulnerable to this overhead fire in ways they were not vulnerable to shells exploding on the surface. But achieving reliable airbursts with mechanical time fuzzes was difficult. The fuse had to be set correctly before firing, accounting for range, charge, weather, and a dozen other variables. Errors were common. Shells frequently exploded too high or impacted the ground before detonating. A proximity fuse that could sense the ground and detonate at a preset height automatically would solve these problems. The artillery officer wouldn't need to calculate the precise time to burst. The shell would burst itself at the right moment every time. Section T engineers examined the feasibility. The radio altimeter circuit in the fuse already detected nearby objects. Ground was simply a very large nearby object. The challenge was tuning the sensitivity so the fuse would trigger at the desired height, typically between 15 and 30 feet, rather than at a much higher altitude where it would be ineffective. Testing began at Aberdeen Proving Ground in Maryland in early 1944. Engineers fired artillery shells fitted with modified proximity fuses at ranges where they could observe the burst height. Initial tests showed the concept worked. The shells detonated at consistent heights above the ground. Refinements improved the reliability and adjusted the triggering height to the optimal range. By summer 1944, proximity fuzzes were being produced for 105mm howitzer shells and 155mm gun shells, the standard American field artillery pieces. But there was still the security problem. Over water, proximity fuses were safe to use because duds would sink. Over land, a dud proximity fuse could be recovered by German forces, analyzed, and potentially copied. The Allied command debated whether the tactical advantage was worth the security risk. The decision came down to timing and circumstances. By late 1944, the war in Europe was approaching its final phase. German industrial capacity was being destroyed by strategic bombing. Even if the Germans captured and reverse-engineered a proximity fuse, they lacked the manufacturing capacity and resources to produce them in meaningful quantities. The risk was acceptable. The first large-scale use of ground-burst proximity fuses came during the Battle of the Bulge in December 1944. German forces launched a surprise offensive through the Ardennes forest, attempting to split Allied forces and capture the port of Antwerp. The offensive achieved initial success through surprise, overwhelming several American units. The weather was terrible. Heavy clouds and fog that prevented Allied air support from operating effectively. German troops advanced, believing they had caught the Americans unprepared. American artillery units fell back, established new firing positions, and began engaging the advancing German forces. But this time, their shells were fitted with the new proximity fuzzes, designated VT fuzzes for variable time, a deliberately misleading name chosen to conceal their true nature. When artillery batteries opened fire, their shells exploded consistently at 20 to 30 feet altitude, exactly as designed. The effect on German troops was immediate and devastating. Soldiers advancing through forest and open ground found themselves under artillery fire that exploded above them. Foxholes and ditches, which provided protection against normal artillery, were useless against airbursts. The shrapnel came from above, raining down into positions that would have been safe from ground bursts. Casualties mounted rapidly. German after-action reports described the American artillery as having achieved impossible accuracy and effectiveness. Some German officers suspected the Americans had developed new proximity sensing technology, but had no concrete evidence. One German soldier, captured after his unit was shattered by proximity-fused artillery fire, told interrogators that his company had taken 50% casualties in less than 10 minutes of shelling. He described shells that always exploded in the air, never on the ground. He said his comrades had tried to take cover, but found there was no effective cover against this fire. The psychological impact was severe. Infantry, who had survived years of combat on the Eastern Front, who had experienced Soviet artillery barrages, stated that American artillery with these new shells was more frightening than anything they had encountered. The effectiveness of proximity-fused artillery in ground combat exceeded even optimistic predictions. Field tests conducted after the Battle of the Bulge compared ammunition expenditure and casualty rates between conventional contact and time fuses versus proximity fuses. The results were stark. To achieve a given level of suppression or casualties against infantry in the open, proximity fuses required approximately 1/4 the ammunition of conventional fuses. Against infantry in prepared positions, the ratio was even more favorable, with proximity fuses requiring as little as 1/5 the ammunition. This had immediate practical implications. Artillery units could engage more targets with their available ammunition. They could sustain fire missions longer before requiring resupply. They could achieve tactical objectives with fewer guns and fewer rounds. From a logistical perspective, this was revolutionary. Artillery, ammunition was heavy and bulky. Moving it to the front lines required trucks, trains, and enormous quantities of fuel. Reducing ammunition requirements by a factor of 4 or 5 meant that logistics units could support more combat units with the same transportation assets. American artillery doctrine in World War II emphasized mass and responsiveness. When an infantry unit needed fire support, they expected artillery to respond quickly and in volume. The proximity fuse made this doctrine even more effective. A battery of 6 105mm howitzers firing proximity-fused shells could deliver the suppressive effect that would have previously required 2 or 3 batteries firing conventional ammunition. This force multiplication allowed the American Army to support more combat operations simultaneously and to sustain operations longer. German forces facing this improved American artillery found themselves at a severe disadvantage. Their own artillery, while technically sophisticated and well-handled, used conventional fuses. They did not have proximity technology. Even if they had captured intact fuses, which they did on several occasions, their ability to reverse engineer and produce them was limited by late 1944. German industry was collapsing under strategic bombing. Factories were being destroyed. Raw material supplies were disrupted. Skilled workers were being drafted or killed. The infrastructure needed to manufacture complex electronics at scale simply did not exist. Some German scientists examined captured proximity fuses and understood the principles involved. They recognized the vacuum tube technology, the radio altimeter concept, and the ingenious solutions to the problems of miniaturization and shock resistance. But understanding the technology and being able to manufacture it were completely different challenges. Germany in 1945 could not build proximity fuses in the quantities needed to matter. Militarily, even if they had perfect technical documentation, the Japanese faced similar circumstances in the Pacific Theater. American forces continued to use proximity fuses exclusively over water throughout most of the Pacific campaign, maintaining security. But in the final months of the war, during the Okinawa campaign and the planned invasion of Japan, proximity fuses were authorized for use in ground combat. Japanese forces defending Okinawa experienced the same devastating effectiveness that German forces had encountered in Europe. Artillery barrages using proximity fuses caused higher casualties with less ammunition expenditure. Japanese technical intelligence services recovered some dud proximity fuses from anti-aircraft engagements, where shells had malfunctioned and fallen intact into the ocean near shore. Engineers examined these fuses and produced technical reports describing what they found. The reports, recovered after the war, show that Japanese scientists understood the basic operating principles. But Japan's industrial situation in 1945 was even worse than Germany's. Strategic bombing had destroyed much of Japan's manufacturing capacity. Raw materials were unavailable due to the American submarine blockade. The country simply lacked the resources to develop and produce their own proximity fuses. After the war ended, the proximity fuse program was declassified gradually. Technical details were released to allow American industry to adapt the technology for civilian applications. The basic principles, radio altimetry and miniaturized electronics, found applications in aviation, navigation systems, and industrial control equipment. The manufacturing techniques developed to produce proximity fuses in large quantities contributed to the broader electronics industry's post-war expansion. The vacuum tube design developed for the proximity fuse, the rugged shock-resistant tubes that could survive being shot from guns, influenced subsequent military electronics development. While vacuum tubes were eventually replaced by transistors and integrated circuits, the design philosophy remained relevant. Military electronics needed to be rugged, reliable, and capable of operating in extreme conditions. The lessons learned in developing the proximity fuse informed decades of subsequent work. More immediately, the proximity fuse saved lives. American ships that would have been sunk by air attack survived because their anti-aircraft guns were effective. American soldiers advancing through Europe faced less effective German counterattacks because American artillery suppressed German forces more efficiently. The ammunition that did not need to be manufactured and shipped because proximity fuses were more efficient freed up industrial capacity and transportation assets for other purposes. The victory in World War II depended on countless factors, but effective technology employed at scale was certainly among them. The development of the proximity fuse represented a particular kind of achievement, one that characterized much of the Allied scientific effort in World War II. It was not a single brilliant insight that changed everything. It was systematic, organized application of scientific knowledge to solve a defined military problem. Merle Tuve and his team at Section T were not working on abstract physics or theoretical research. They were solving an engineering problem with life-or-death implications. The proximity fuse succeeded because it combined several elements that were individually available but had never been integrated in quite this way. Vacuum tubes existed. Radio technology existed. Miniaturization techniques existed. What was new was the specific combination, refined and hardened to survive conditions that would destroy conventional electronics. The achievement was as much about manufacturing and reliability engineering as it was about innovation in basic science. This reflected a broader truth about World War II. The conflict was decided not primarily by which side had better scientists or more creative engineers, though those factors mattered. It was decided by which side could take scientific knowledge and convert it into operational military hardware at scale. The Germans developed many sophisticated weapons, including jet aircraft, ballistic missiles, and advanced submarines. But they developed them late, in small numbers, and often with reliability problems. The technology itself was impressive, but operationally insufficient. The Americans and British developed weapons that were good enough, manufactured them in overwhelming quantities, and ensured they were reliable enough to work consistently in field conditions. The proximity fuse epitomized this approach. It was not the theoretically optimal solution to the anti-aircraft problem. A more sophisticated design with more tubes and more complex circuitry might have been slightly more effective. But it would have been more expensive, less reliable, and impossible to manufacture in the quantities needed. The Mark 32 and Mark 53 proximity fuses were good enough and could be produced by the tens of thousands per week. By the end of the war, American industry had manufactured over 22 million proximity fuses. 22 million miniature radio sets, each one capable of surviving being shot from a gun, each one containing 5 vacuum tubes and a complete radio circuit, each one produced for roughly $25. This was the real achievement. Not that the technology was possible, though proving that required brilliant work, but that it was producible at industrial scale with consistent quality. The sailors on the USS Helena who watched their 5-inch guns destroy Japanese aircraft in January 1943 could not have known any of this. They did not know about Section T or Merle Tuve or the years of development work. They did not know about the shock-resistant vacuum tubes or the centrifugally activated batteries. They only knew that their guns were suddenly hitting targets, that the ammunition was working in ways it had never worked before. That was enough. The technology worked, and that made all the difference. For the Japanese pilots flying against American ships, The improved anti-aircraft fire meant higher casualties and lower mission success rates. They could not know why American ships were shooting better. They only knew that the odds of survival had worsened. For German soldiers sheltering from American artillery during the Battle of the Bulge, the airburst shells that exploded consistently overhead were terrifying, not because the soldiers understood the technology, but because they understood the effects. The shells were killing men who should have been safe in their fighting positions. War drives technological development in ways that peace does not. The urgency of combat, the immediate life or death consequences of technical success or failure, focuses effort and resources with unusual intensity. The proximity fuse would likely have been developed eventually in peacetime, but it would have taken decades rather than years. The war compressed the development timeline, mobilized the necessary resources, and overcame the institutional inertia that normally slows innovation. But the proximity fuse also represented something else, something that would become increasingly significant in the decades after World War II ended. It was an early example of electronics being used to solve problems that had previously required human judgment and skill. A gunner with a mechanical time fuse had to estimate range, calculate flight time, and set the fuse accordingly. A gunner with a proximity fuse simply fired. The shell made its own decision about when to detonate based on its electronic sensors. The human role was simplified. The technology handled the complexity. This pattern would repeat and intensify in subsequent decades. Guided missiles, computerized fire control systems, automated navigation, all represented the same basic principle. Electronics could handle tasks that previously required skilled human operators, often more quickly and reliably than humans could. The proximity fuse was an early step in this direction, a small electronic brain inside an artillery shell, making a simple but crucial decision. In 1943, this was revolutionary. By the 21st century, it would be routine. The physicists and engineers who developed the proximity fuse could not have predicted these long-term implications. They were focused on the immediate problem, making anti-aircraft guns effective against attacking aircraft. They solved that problem successfully. In doing so, they created a technology that would influence military systems for decades and contribute to the broader development of electronics and automation. The proximity fuse was simultaneously a solution to a specific wartime problem and a glimpse of a future where electronics would mediate human interaction with increasingly complex systems. The story began with a destroyer off Guadalcanal, firing shells that exploded near their targets instead of in empty air. It ended with American victory in World War II, achieved partly through technological superiority deployed at industrial scale. The proximity fuse was one technology among many that contributed to that victory. But it was emblematic of a larger pattern: the systematic application of scientific knowledge to military problems, the conversion of laboratory prototypes into mass-produced weapons, and the willingness to invest resources in solving problems that seemed impossible until they were solved. For Merle Tuve and the scientists at Section T, the proximity fuse represented years of intensive work under enormous pressure. For the workers at Eastman Kodak assembling the fuses on production lines, it represented employment and contribution to the war effort. For American sailors manning anti-aircraft guns, it represented survival. For Japanese pilots and German soldiers on the receiving end, it represented a new and effective threat. For historians examining World War II decades later, it represents one example among many of how industrial capacity, scientific knowledge, and organizational capability combined to determine the outcome of the greatest conflict in human history. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.